Okay, so we start the divergence theorem. So what is divergence? Remember in calculus 2, you saw the word divergence. It was about convergence and divergence, for example, of improper integrals, of sequences, of series. Now divergence is a different term. So we will see what we mean by divergence. At least we will see the mathematical definition. In another video, I will discuss the geometric meaning of divergence in a similar way to the curve somehow. So what is the divergence theorem and what is its connection with our previous example? So remember, in this example, we had a function of, we had a sphere, the unit sphere. We computed the surface integral of this function over this unit sphere, and in the end, after all these computations, we reached the answer for pi over 3. And in this example, we commented on this final answer that it is equal to the volume of the sphere. So we ended by asking, is this somehow related to the volume? Is there any relation between the surface integral and the volume of the sphere? So this is understood by virtue of divergence theorem. So the theorem says, so the divergence theorem, first it connects the surface integrals with triple integrals. And I'm sure at this stage, many of us remember how curve integrals are connected to double integrals using Green's theorem. So just to remind you, Green's theorem, it is a tool that converts, to remind you, the surface, the curve integral into a double integral like this. This was the formula for Green's theorem. Now, divergence theorem, it connects the surface integrals. So this is the role of the divergence theorem. It connects surface integrals with the triple integrals. Now, as we did in Green's theorem, does a Green theorem mean that curve integrals are easily computed using double integrals? Not necessarily, it depends. Sometimes double integrals are easier to compute, while in other cases, the curve integral is easier. The same for surface integrals. So the divergence theorem, it is a tool that we can use sometimes. We will see that sometimes triple integrals are much easier than the surface integral itself, while in other cases, the surface integral and the parameterization, the normal method, is easier than the triple integral. So the statement of the theorem, the statement of the divergence theorem, it says, of course, we're assuming all the time our functions are smooth, they are continuous, they are partially differentiable, and so on. The same for our surface. So basically, if you have, let us be a closed surface. This reminds us of the term closed curve in Green's theorem. So we need to clarify the meaning of a closed surface after we finish the statement. So if S is a closed surface and F be a smooth vector field as a vector valid function, then the divergence theorem says the surface integral of f dot n dA is equal to the triple integral of divergence of dV. Where? So we need to discuss the notations used in this formula. First of all, as a triple integral, any triple integral needs a region of integration. So there is a region of integration, let's call it T. Where? What is T? T is the solid inside S. What is divergence of? This is the first time we see this notation in this course. So divergence of is we take the first component of f differentiated with respect to x, the second with respect to y, and third with respect to z. What is dv? dv is the standard dx, dy, dz, of course, in any order. Again, can we say in any order? Yes, because we're assuming our functions are smooth, so the divergence itself is continuous, and when the function is continuous, there is no difference in the order dx, dy, dz. You can write it in any order. You have 6 orders for that. Not only this, okay, so so these are the notations used in the right side of the formula. But what about the left side? Remember, now as a triple integral, we just have one answer. So if we are 40 students, we're computing this right side, we'll get one answer, of course, if our solution is correct. But for the left side, remember, we can have 2 different answers depending on the n. So for example, if we go back to the unit sphere example, we solved this example using the outward normal vector. And in this case, our answer was 4 pi over 3. But in the same example, if we used the inward normal vector, that would give us negative 4 pi over 3. So we are facing this formula where we have 2 sides. One of them is always having the same value, while the other one depends on the orientation. So we need to clarify the n. So what is the n? The n will be the outward normal vector. This is very important. So in applying the divergence theorem, we need to ensure that the normal vector is the outward normal vector. And of course, this reminds us of the previous example on the sphere. Remember, we had kind of the same scenario when we dealt with Green's theorem, where Green's theorem has 2 sides. One of them depends on the orientation of the curve. So we had, at that time, we had to discuss the orientation of the curve in Green's theorem, while the other side of Green's theorem is about a double integral which has the same value all the time without any orientation. So this must be clarified. Now, what do we mean by a closed surface? A closed surface, we mean something like a full sphere, for example. This is a closed surface. Now, if we talk about the cone like this is not closed, but if we close it, if we add the top, it becomes a closed surface. If you talk about the cylinder, to be closed, you must include the bottom and the top. So this is the meaning of a closed surface. For example, so all these are closed surfaces. On the other hand, for example, if you take a plane, this is not closed. If you take a cone without, so if this is only my cone without the top, it's not. If you only take the hemisphere, the upper, for example, hemisphere without the bottom, these are not closed surfaces. So in the first three curves, surfaces, sorry, you can apply divergence theorem, while in the other 3 cases you can't because the surfaces are not closed. So this is the meaning of a closed surface. Then, what do we mean by the outward normal vector? For example, of course, outward, inward, that means we're talking about closed surfaces. If you're talking about the unit sphere, this is the outward normal vector. If you talk about the cone, this is the outward normal vector. For the cylinder, on the lateral faces, this is the normal vector. On the top, it's the upward normal vector. And for the bottom, it's the outward normal vector, the downward normal vector. So this is the meaning of the outward normal vector. And the best thing to do to clarify this is to solve an example. So example on the divergence theorem. And I'm going to solve, so let f be x squared y squared z, and let's compute the surface integral where S is the unit sphere oriented. So what's the orientation? So that n is the outward normal vector. And by the way, this is usually called the positive orientation. So if you hear this term, what do you mean by the positive orientation of the surface? That means we're talking about, sorry, this word orientation is written in a very bad way. So positive orientation. So if you hear the term positive orientation of a surface, that means you're dealing with a closed surface where the normal vector is pointing outward the surface. Okay, so let's solve. So we're having our sphere as our surface. It is a closed surface. And we're asked to find the surface integral. Now the divergence theorem says, okay, if you're computing, so this is the divergence theorem, if you're computing a surface integral, instead of doing the surface integral, convert it to a triple integral. Again, is it easier to do it using a triple integral or not? That depends on the different scenarios we have. It depends on the surface itself, it depends on the function and the computations. So as long as we satisfy all these conditions in the divergence theorem, so the surface is closed, yes. The function is smooth, yes, we're dealing with basically polynomials. So basically, this becomes the triple integral dv over t. What do we mean by t? T is the solid inside the surface. So this is the region of our triple integral. So this becomes the triple integral. I'm going to draw it like this. What is the divergence? This is the definition of the divergence. So you take the first coordinate of the function, you differentiate it with respect to x, that's 2x. The second differentiated with respect to y, the third differentiated with respect to z dv. And now you compute this integral. Now again, is this an easy triple integral? It depends how you look at it. If you want to do all the computations, since you're dealing with a spherical region, the best way to do it is using spherical coordinates. But instead of looking at it using spherical coordinates, we can say, okay, this is the x-axis, the y, and the z. We can easily see that this region of integration is symmetric with respect to the x, to the y, to the z values. So when we say the integral, the triple integral of 2x, that will give us 0 because half of the values in this sphere are positive x values, half of them are negative y values, the same for y. So we are left with the triple integral over the sphere 1 dv, which is the volume of the sphere, which is 4 pi over 3 times the radius cube, which is what we got in our previous example. Remember when we did this example using the normal parameterization method, we got this answer. And in that example, we asked if there is any relation between this answer and the volume of the sphere. Now we can see the relation. So the relation comes as a result of the divergence theorem. So this is how we apply the divergence theorem in case of the sphere.